So exercise 2 you should have tried on your own before coming here. But in this case, we're looking at the amount of money you could win from a card game and the probability of those occurring. So remember, you want to start with figuring out what are the different amounts you could win. So reading through this, you could win nothing. So there's our first outcome, 0. If you get a spade, you could win $5. So there's our second outcome. If you get a club, you could win $10. So we got 10. And then the last one, this is the only place that you might have had a mistake. You get an extra 20 if you get the ace of clubs. So that means we're going to add this 20 to the 10. So your last value should be a 30, not a 20. Second piece is to figure out your probabilities. For those of you who are sitting there worried because you don't know a deck of cards very well, don't worry. I never put these questions on exams because I don't want you to have to memorize what a deck of cards is. But a red card, well, that's exactly half the deck, 2 of the 4 suits, 26 of the 52 cards. Any of those fractions would be perfectly fine. For a spade, that's 1 of the 4 suits in the deck, right? Or 13 of the 52 cards. For a club, you win $10, but you get an extra 20 for the ace of clubs. So there are 13 clubs. 1 is the ace, which means there are 12 clubs that will give us, out of the 52 cards in the deck, $10, and 1 card that will give us $30. So this is what your probability distribution should have looked like. But again, if you're not somebody who knows the deck of cards really well, don't worry. I won't write a question like this on the exam. So the next thing we need to be able to do is to find the mean and standard deviation of this sort of distribution, because we can figure out what the average amount somebody would win for this game is, and we can figure out the standard deviation, or how much variability there is in the amount they would win. So that's what we're going to do in exercise 2. We're going to find the expected value, which is another way to say the mean, and the standard deviation for our game. So let's start with our expected value. We do have these formulas. This will be on the formula sheet that I give you on the exam. So we're going to use them. So e to the x, or this is expected value of x, which is our mean. Remember, our sigma notation from way back in part 2 says we're going to add up all the stuff that comes after, and after this we have x, which is the outcome, times its probability. So first outcome is 0, and its probability is 1/2. And then we're going to add that to the next outcome, 5 times its probability. Add that to the next outcome, and its probability multiplied together, and finish that up. So if you do all this in your calculator, you should get 4.1346. Now, one thing here is that people really like to round this. You should not. One, we're going to use this in our next calculation. You can see that there's a mu in both of those, so we want to make sure we keep at least 4 decimals. And 2, even if our units don't make sense for decimals, we're talking about this long run average. So if we were to write down what the heck this tells us if someone was to play the game in exercise 2 many, many times, they would win an average of $4.13 with this extra little bit each game. Now, they obviously can't win $4.13 in a particular game because, as you see, that's not an outcome, right? But if they played it a really long time, this would be the average over the long term. So this is usually what you see when you're calculating odds in, say, Vegas, as how the house sets a price. So if this was a game in Vegas, the house would charge more than this, maybe $5, because if they charge $5, now they're guaranteed in a long run, because they are going to play every single game of this, that they're winning about 87 cents each time. So that's how those odds are set and how those payouts are set, so that their expected value is below what you are paying. But as somebody who's only playing the game once, you don't really care about this long run expected value because you're hoping to get something else, and you're looking at the one-time odds. All right, so the second piece is the standard deviation. So how much variability is there in this particular payout? Like how much does the house have to worry about maybe ending up losing money versus winning money? How much variability is there for you? That's obviously very important because for you, you want to see higher variability because you'd like this to happen more often. So that's what the standard deviation comes in. There are two formulas you could use. One has the same feeling as what we saw back when we saw this in part 2. How far is each value from the mean? Square that. And then essentially for both of these, what we're doing is we're just weighting them based on that probability. So 0 is the most likely, so it gets the biggest weight. 30 is the least likely, so it gets the smallest weight. So the same thing is happening here. So how far are things from the average, and then how much weight do they actually carry? Because if they occur more often, we want to give them more weight. The second formula, while it's not as easy to understand, is easier to calculate. So that's the one we're going to use to actually calculate this. So this formula, I'll write it down, even though it's right above. Oops, that's terrible. Multiplication symbol. The beginning, we can see, very similar to our problem over here. Sum up every x but squared times its probability. So we're basically going to redo that original thing that we did here, right? We'll have 0 squared times 1/2. The only difference is we're squaring each of the values. So that gives us this piece. Bloop. And then we're going to subtract off our mean squared, which is why I said it's important to keep more decimals. And then we're going to take the square root of the whole thing. That's what we're looking at. So I would just do this piece first. So I'll go ahead and bring up a calculator and do this by hand so you guys can see it. Dun, dun, dun. So I don't really, 0 times anything 0, so I'm not going to bother with that. 5 squared divided by 4 plus 10 squared times 12 divided by 52. Oops. And then, oops, I forgot to do the plus 30 squared divided by 52. I could do times 1 over 52, doesn't matter. So that's what we get for the first part. Then I subtract off 4.1346 squared, and then we're going to take the square root of all that business. Cool. So square root of the answer. So our standard deviation here, 5.4350. So this still has the same units in terms of its interpretation. It still has dollar signs. It's how much variability we expect to see. Remember, we don't expect to see things much outside of 2 standard deviations or 3 standard deviations from the mean. In fact, back in part 2, we had Chebyshev's rule, which gave us some cutoffs, even for something that wasn't symmetric, which this is not. So, again, this tells us that it's very unlikely that we're going to see any of the winnings in the 30 range. But 10 is not unusual or uncommon, and 0 is not uncommon either. Alright, so I'm going to do a separate video where I show you how to do this in a calculator shortcut. So if you want to see a calculator shortcut, watch the next video.